Hi there. Today we're going to take a look at the OpenAI Microscope and this article on Distill called Feature Visualization. So the Feature Visualization article is by Chris Ola, Alexander Mortvintsov, and Ludwig Schubert of the Google Brain team, while the OpenAI Microscope is by OpenAI. So keep that in mind. These tools are tools for visualizing what neural networks learn. And specifically here, we're dealing with image classifiers, and even more specifically, ImageNet classifiers. So you know ImageNet is this big data set with 1,000 classes of images, and the images are somewhat like 200 by 200 pixels, and you're just supposed to put them into one of these 1,000 classes. And networks have become really good at these kinds of things. So our question is, what do these networks learn? And there are a number of very cool works that have started to investigate what these networks learn. So this started with work like Deep Dream, or even before that, but this is a very good summary and also overview of this. So in this article, they first showcase these patterns here, where you can see that as you go through the network in the layer, this is layer conv to the 0, which is a very low layer in the network. You have things, what looks like pattern detectors. So these are the things that the network is excited by. And we'll get in a second at how you create these things. Just be sure these are the things that these particular layers in the networks are most excited by. So this layer is super excited by these textures, right? But as you go higher, the network gets excited by these kind of textures. Then it gets excited by more complex things, right? So the pattern is, the higher you go in the layers, and people have been seeing and claiming this and measuring this since RBF networks and whatnot, that the higher you go in these networks, the more complex features that they build. So they always build, the hypothesis is they build very complex features from the lower layers, and the lower layers, they have less and less complex features, and until you're the very bottom layer, they simply extract edges and patterns of texture like this. Whereas in the top layers, all of these are hierarchically assembled to give you very, very intricate features. So these usually look pretty funky. That's why I like to investigate. So this article focuses on how is this done, and the answer is by optimization. Now, what do we mean? I actually have the article here somewhat printed out, but the graphics, they don't really print very well to the notebook here. So imagine this here. So what you want to do is you want to see how much activation is in the network for a particular input. And you can do this in many, many different ways. The easiest form, let's actually start over here. If you have a neural network here, and this is the softmax classifier, and these are the classes. In this case, let's say this is dog, this is cat, and this is car, house. Let's go with house. You can think of, okay, I want to know when the network sees a cat. What does the network think of cats? So what I would do is I would take an image that is just noise, right? Just random noise, like this one on the left here. And I would start to optimize using backpropagation. I would start to optimize this image. Now, you usually know backpropagation as the thing that will optimize these weights if we have given an image and a label, right? But right now, you have to, and we optimize the weights here. Sorry, I should theta, right? But right now, you have to rethink what we have given is the label and the weights, we keep them constant, but we optimize the input image to maximize this label as much as possible. So we ask of X, please update yourself such that the output is as much cat as possible, right? And then we just optimize for that. And so we hope that this picture would turn out to be as much cat as we like, right? And usually here, I don't know exactly which class they have here, but you won't get a cat. Sorry, over here. You won't get a cat, or here if you optimize the logits, it's the same, just you do the same thing before the softmax. What you will get is some weird trippy thing. So in our classifier, you might get something like, there's a cat here, but there's also one here, right? Because two cats are more cat than one cat, and there's like a giant cat head here, and inside the cat head there is another cat head, and there's like a cat tail somewhere here, and again there's a cat eye right here. So you get like something super trippy that is as much cat as possible. All right, now this is somewhat interesting, because you can find out what does the network think is the most cat-like thing there is and the most dog-like thing there is. But what you can also do is you can see what do the intermediate layers of the networks, what do they get excited by. So what you can do is, for example, you can take an individual neuron in one of the layers, right? So this here might be a convolutional layer with its convolutional filters, right? And these are the different channels of the convolutional layer. And then this thing here is just a single neuron there. And what you can do is you can say, okay, X, we have now, again, we input the image X, and we optimize the image X such that with the given weights, this particular neuron, let's call it N, and N is maybe this neuron right here, right? This particular neuron is as much activated as possible, right? So we no longer optimize for a label, but we optimize for a particular neuron to be activated as much as possible. And then we can sort of see what is an image that activates this neuron as much as possible. In this case, that thing. You can actually do the same thing with an entire channel if you simply say when is the channel as a whole activated as much as possible. And something like Deep Dream did the same thing, but with an entire layer in the neural network. Like, what is this layer activated by? Now you can imagine there's not only one image that activates it the most, but probably depending on your start here, you'll get different results for depending on where you start, and we'll go into that later as well. So these are the kinds of things you can do to investigate these neural networks and see what they pay attention to in each of the layers, right? So let's go on here, and so they say, okay, if we optimize by optimization, you get something like this here on the bottom row. Looks pretty funky, right? But what you could also do is you can visualize by what is called dataset examples. And with dataset examples, you don't do this thing. You don't do the optimization procedure, but you go into your database, into your data set, and you find the images that activate, so the XI from your data set, that activate a particular neuron the most. So you simply sort all the images in your database and you just pick the 10 or so that activate that particular neuron the most. And that would also give you an understanding. It's actually a valid thing, and the AI microscope combines both of them. So on the bottom you see what particular neurons are most excited by, and at the top you see that the dataset examples they're most excited by. So you can see that there's a healthy diversity in the dataset examples, but they also all kind of map to the what it's most excited by. It's pretty cool. The last point they make in this article is that of diversity. With the dataset examples, you do get naturally sort of a diverse set of images, of course, where you can guess. You can also say, okay, what are the maximum activations and only slightly positive. You can even give negative examples. But with the positive, you can only either maximize fully, or you can, take the negative and you can say, okay, what is this neuron not excited by at all? But you won't get kind of a spectrum of what the neuron is excited by, or the unit or the layer. And what they're doing is simply they add a diversity term. They say that works best. So what does that mean? It means that here, if we optimize X and Y, right? Let's go up here. If we optimize X in that, right, and try to maximize the activation of N, we don't want to do X by itself, but what we want to do is we want to do an entire set of Xi, right? So we feed an entire mini batch in there, and we want to maximize N, but also maximize a diversity term. Let's call that D between the X1 to XB, right? So you want to maximize the activation of the neuron, but at the same time in your loss function that you optimize, you also have this diversity term where you say the images that you produce should be far apart from each other, or kind of apart from each other. And thus you do get diverse samples. Okay, the printing again doesn't work. So here you see that if you just simply optimize, you get the thing on the left. But if you have a batch of things and you optimize them to be diverse from each other, but also activate the layer or the unit, you get a variety of high activations. And you can see here that this is some sort of curve. This could be a beak of a bird, but on the right here, this could also be kind of a snout of a monkey or something. Okay, so it's just curvy things that is activated by. Here they give another example. You can clearly see that there is like some sort of eye in the picture, but then if you optimize with diversity, you can see that some of them do not have this eye thing, and in fact, also some of the dataset examples do not have this eye thing. So it might be interesting to optimize here with diversity. And even they say in higher layers, it gets even more diverse with what you achieve with this ball detector. They also say they research interactions between neurons where they can interpolate between them, right? So you can here have two different units. Let's say this top left one here is the thing that we've just seen with the curvature activator. And then on the right, we can select this thing here that appears to be activated by these bird-like things. And if you optimize an image that activates both of them, you get the thing on the bottom left. And this is very good for understanding how neural networks work, because what a neural network will do is it will take the thing on the top left and the top right from lower layers, and it will combine them to form features of higher layers. So while the top right thing looks like generic birds, the bottom left thing looks much more like birds with, let's say, long necks and kind of curved necks, so more stork-ish birds, right? Because we've added in this curvature thing. So this is very, very cool to play around. You can also here interpolate between two neurons, like you would interpolate in a GAN, right? And yeah, so they do make a point of regularization. I don't want to go into that particularly, but you have to be careful. You can't just apply the optimization procedure as I said right now. You actually have to do some regularization and to get rid of what are essentially adversarial examples in this process. because if you just straight up optimize, you will get pretty high frequency, crappy results. I actually want to jump over now to this OpenAI Microscope. So this is a tool that lets you explore these visualizations. So at the beginning, you can pick one of these models, and I'll pick Inception V1 just because some of the other ones, they don't have everything done quite yet. All the visualizations. So on the right here, you can actually see the architecture of the network. If you know what an inception network is, this is what it looks like. And you would be able from here to select one of these units straight away. But I'm gonna, we're gonna go to the left here. So you have Deep Dream activated, which means the entire layer is optimized for. So per layer on the right side, you have an image here. And you can already see that if we go from the bottom, what we saw before, we get patterns that become more and more complex as you go up the layers, and then more and more until you finally have what the network appears to be most activated by is mostly dogs, which is okay because ImageNet is dominated by dogs. So you can click on any of these right here, like this one, and now you'll be able to inspect the individual nodes in this layer. So before we had the whole layer, right? The whole layer was activated by something, but these layers, they have different channels and also different neurons within the channel. So you can select this here. You can go neuron activation or channel activation. And these are the images that these channels are excited by the most. You see, you get pretty funky pattern. If we select one interesting one, maybe this one right here, you can see on the left, this is the channel optimization. On the right, this is the neuron optimization. And here you get the dataset examples that are most activated, that mostly activate this particular channel or neuron. So, sorry, this particular, channel. So you can see this is pretty similar to the thing I drew, where except for it being a cat, it's some sort of a fox dog thing, right? And you can explore the neural network in this fashion. So you can go through the layer here and look at units. This seems to be a whiskers classifier, and lo and behold, things with whiskers will activate the neuron. And as you go up the layer, and this is the cool thing, right? So right now we're here in this layer 4. As you go up, you will see more and more intricate patterns of activations. I could play around this for very, very long time, but I won't waste your time too much. There is a Slack workspace where people discuss interesting patterns. Oh, look, there is a. What is this? Okay. Yes, this is some sort of temple constructor. Very cool. There is a Slack workspace where people discuss interesting things. For example, they discuss how the car detector that you see right here is one of the units. There's literally endless units to look at that detects cars, can be clearly seen to be built from lower level features, such as this wheel detector. You see this wheel detector here is the unit 337 in the mixed 4 layer. And this car hood detector right here is unit 237, also in one of the layer 4s, right? So these are both from layer 4, and then the car detector, I actually haven't looked this up, is in layer 4 as well, but let's check it out. this is in layer 4B, this is in layer 4B, and this is in layer 4C. So you see, this was a risk. The car detector is built from lower level features of car hood and car wheel, right? The car wheel right here detects wheels, and the car hood detector detects hoods, and then the car detector detects cars. So there are I really invite you to go look at it, check out what people find, and explore these models. All of this is based on this Lucid library right here. Also invite you to check that out, where you can perform such optimizations yourself. I will link to that. And with that, bye-bye.